start, I have an announcement to make. The Junior League of Monterey County is offering a $5,000 scholarship for women residing in Monterey County. And this scholarship is for any woman who is 18 years old or older, is involved in the community. All you've got to do is to describe your community involvement, write a personal essay regarding your community involvement, your past academic performance and future goals, and then if you're chosen as a finalist, there's going to be a personal interview. And the deadline for this scholarship application is April 17th. So I encourage all of you women to apply for the scholarship. So you don't need to. Okay, so if you're interested, you can go to this website for more information.
Ask questions.
Okay, so we left Tuesday's class with this question. So I know half the class did histidine, the other class did, the other half did lysine. Which half did histidine? So was this half? Okay, so you guys did histidine. And this half of the class did lysine. And you drew a titration curve for each amino acid. I think we determined on Tuesday what pH you could use to separate a mixture of histidine and lysine. The only thing we didn't do was determine the starting pH for each amino acid and the pH at the last endpoint. So, did you guys do that calculation? Okay, I'll just give you the answer. So for histidine, the starting pH is 1.41. And then the pH at the third endpoint that's equal to 10.8. And then for lysine, the starting pH is equal to, let's see here, 1.59. And then pH at the third endpoint is equal to 11.5. Oh, I was going to ask you guys how to do that. So, how do you guys do that anyway? What's the method? Yeah, so you need to do that equilibrium calculation. What equilibrium constant do you need to calculate the starting pH? So this is a triprotic acid. So the equilibrium constant you need to calculate the starting pH is it Ka1, Ka2, or Ka3? Ka1. Yes, you need Ka1. To calculate the pH at the third endpoint, what equilibrium constant do you need to use? Which Kb? Kb1, Kb2, or Kb3? Pardon? Kb1. It's actually Kb3. Okay, so let's do this calculation for, let's see, which side of the class asked anyway? Lysine. Okay, so what's the Ka for lysine? Okay, so for lysine, let's see. Lysine, we'll just call it, just in general, so we don't have to draw the structure, we'll call it HA3. Okay, sorry, H3A, because it's a triprotic acid, so that's going to associate the H plus and H2A minus. So Ka1 for lysine is equal to, well, we can do it this way. We look at the pKa, so pKa1 for lysine is equal to 2.18. So that means Ka1 is equal to 10 to the minus 2.18 power. And when you do that calculation, Ka is equal to 0.0066. Okay, so we want to do a equilibrium calculation, so we have our initial amount, the amount that reacts, the amount of equilibrium. So for these calculations, our initial concentration is 0.1 molar. Okay, so we'll have 0.1 molar here. And then 0 and 0, and we've had a little bit of practice doing this, so the next step.
Put the X.
Okay. And then equilibrium. Okay, so then we can use our equilibrium constant expression and plug in these values into that equation. So we have Ka, so Ka1 is equal to, let's see, H plus times H2A minus divided by H3A. Now remember that these concentrations are in equilibrium. So we plug in our equilibrium concentration, so that's going to be X times X divided by 0.1 minus X. And this is equal to 0.0066. And then we'll solve for X. So when we solve for X, see, I did this last night. And let's see. For lysine, this turns out to be X equals 0.0257. And note that X is equal to the equilibrium concentration of H plus, so this is also equal to H plus. So to calculate the pH, the next step is take minus log of this number, and when you do that, you should get 1.5. Okay, so should we do it for K for the pH at the third endpoint, or do you guys know how to do that?
The KW, when you're trying to find KV, the KW is always the same thing.
KW is 1 times 10 minus 14. Okay, so any questions on pH to the third endpoint? George? No, that's what I'm asking. I'm asking you guys not to do it. Because if you do it, then I don't have to show you guys that. You don't know how to do it.
So you do another equation like that, and then have KV, and then you're gonna have the A minus instead of the now.
Okay, so you want me to do the KV. Let's do that one for, we'll do this one for histidine. Since I want to make sure each side of the class gets equal treatment. Okay, so for histidine. Okay, so yeah, this was supposed to be 10.8. Now, histidine also is a triprotic acid, so you have H3A, then that goes to H plus and H2A minus, and then the H2A minus goes to H plus. And what's the conjugate base of H2A minus? HA, yeah, 2 minus. And then HA2 minus goes to H plus and A3 minus. So at the third endpoint, which substance will be present? Yeah, so at the third endpoint, this substance is going to be present. At the first endpoint, which substance is going to be present? Yeah, this one will be present at the first endpoint. At the second endpoint, this is present at the third endpoint. So at the third endpoint, we want to figure out that the A3 minus, the conjugate base, react with water. And what are the products of this reaction? Yeah, HA2 minus and OH minus. And we want to figure out KB, so KB for this reaction is equal to KW divided by K. Now, is it KA1, KA2, or KA3? Okay, KA3. Now, note that this KA refers to this acid, HA2 minus. So if we plug in our numbers, let's see, for KW, that's 1 times 10 to the minus 14. Let's see, so that's 1 times 10 to the minus 14 divided by KA3, and KA3 is equal to, let's see, for histidine is okay, so Ka3 is equal to 10 to the minus 10.53 power. Okay, because this is the pKa. This is pKa3 of histidine. So Ka is equal to 10 to the minus pKa power. So anyway, when you do the math here, 10 to the minus 14 divided by 10 to the minus 10.53 is equal to 10 to the minus, let's see, what is that? Minus 14 minus a minus 10.53 is equal to 3.47. Did I do my math correctly there?
3.39 times 10 to the negative 4.
3.39 times 10 to the minus 4. Okay, so now we do an equilibrium calculation again. So we have the initial amount, the amount that reacts, the amount of equilibrium. So what's going to be the initial concentration of A3 minus? Now remember, we started with a 0.1 molar solution of H3A. And in your titration, we're going to see 3 endpoints. And let's see here. So initially we have 20 milliliters of 0.1 molar H3A. To get to the first endpoint, what is the volume of base we need? Okay, 20. So we have 20 to get to here. To get to the second endpoint, we have to add 40. And to get to the third endpoint, we've got to add 60. So note that we have a total of 80 milliliters of solution. So we have to account for dilution. So we have 20 milliliters. 20 milliliters of 0.1 molar. And now we have 80 milliliters of our new concentration. And we solve for C dilute. Excuse me, that's equal to 0.025. Okay, 0.025. So C dilute. So the initial concentration A3 minus is equal to 0.025. And what's the next step? Okay, so we'll plug in our variables. So let's see, here's going to be 0 and 0.